the original activation functions were all sigmoid functions because going back to that biological, like you said, it's either an all or nothing. It's a 1 or 0.
Right.
And so they wanted to kind of illustrate that using a sigmoid function.
Okay.
And a sigmoid function is based on the fact that there's an S shape in the function. So our first one is the logistic function. So I'll write this down. Very good when using a binary classification. Very good. Even using your hidden layers to just send that 1 or 0 to the next node. So the logistic function is, by formula, 1 over 1 plus e to the negative z. And this is going to be our s of z. And graphically, this looks like, here you go here, s of z. This is bounded, and this will be z, by 1 is the upper bound, 0.5 is the y-intercept, and 0 is the lower bound. So I'll draw our nice S shape that goes through y at 0.5 and asymptotes at 0 and 1. So one more thing to write here is 0 is less than s of z is less than 1, and where z is less than negative infinity and is greater than negative infinity and less than positive infinity.
And if I may,
absolutely.
Layne, I just want to make sure here we're gonna make sure that we write that little mark on the z just to
yes, to make sure it's not 2.
Yeah, and then I'm just gonna push this mark for the -1 a little bit higher, just to accentuate the point that this is an asymptote.
Yes.
Right. So this is 1. Okay.
That's a good point. That looks good.
Okay. So I hope that everybody can understand why the logistic function crosses the y-axis at 0.5, because at z is equal to 0, e to the -0 is equal to 1. So then the denominator becomes 2, and 1 over 2 is equal to 0.5. So that's why this y-intercept here is 0.5. Okay, so that's our logistic function as an activation function, and so we have a few other activation functions to review.
Yep. Okay. And before we hit the other activation functions, I want to say that this logistic function is very, very popular, especially when we're doing classification. So let's say we have a cat classifier, and we have a whole bunch of examples of the pixels that are coming in as our inputs, and we want to know whether it's a cat or it's not a cat. And so our output, based on all of the pixels, and after going through the hidden layers and being transformed and having that complex representation, will come out the y-hat as maybe something like 0.98, meaning that it's 98% chance that this is a picture of a cat.
Right.
And so that's how you'd use that. If you wanted to have multiple categories of outputs, let's say you are trying to predict the model of a car or the make of a car, and you had 10 choices. You could have 10 different outputs that each have a 0 or 1, and after going through, it would say this is an 80% probability it's an Acura, a 10% probability that it's a Dodge pickup, etc. So you can start playing with this and creating the architecture of this model based on your inputs and how you want it to predict the output.
And I think it's important to point out for a multi-category classifier where there are many categories, 2 or more, the probabilities for all of those categories must sum to 1.
Yes.
Right?
Yeah.
And by default, most binary classifiers classify something as 1 if it's greater than, if the probability is greater than 0.5, and as 0 if the probability is less than 0.5. But that's the default classification rule. You can create whatever rule you want, right? So the hard part for the neural network is predicting the probability of success. Okay. I feel badly about where I put this mark, and it probably should have been a little bit lower than that. Okay.
That's okay.
Probably somewhere there. Okay.
And we'll rewrite this with the next sigmoid function coming up.
Okay. So that's the logistic function with asymptotes at 0 and 1 and crossing the y-intercept at 0.5. Okay, so the next activation function, Layne.
Yep, the next activation function we have is the hyperbolic tangent function.
Okay.
So So this one is f of z equals tan h of z, which equals e to the z minus e to the negative z divided by e to the z plus e to the negative z. And this looks like very similar to the other one, but our bounds are now at -1 and +1. Make sure that shows as a 1, with the intercept being at 0 here. And we'll draw the graph, a nice.
Okay.
Hopefully that.
Yeah, that's good. No, that's good. Yeah.
And quickly here, f of z is bounded by 1 and 0. Sorry, -1.
Yeah.
And z is again bounded by +infinity and -infinity.
Mm-hmm. And if you don't mind, then just put the marks on the z here and the z
yes.
there. Yeah.
Inconsistent. That's strange. Yep.
Yeah. Great. Okay. So the hyperbolic tangent function. It looks very similar to the logistic function, except that the lower bound is at -1 rather than 0.
Yeah.
Okay. And it crosses the y-axis at z is equal to 0.
So with this function,
sorry, it crosses the y-axis at 0. So
at 0, yes. Yeah. Let me actually put the
at f of z is equal to 0.
F of z.
Yeah, it crosses the y-axis at f of z is equal to 0. Sorry about that. Okay, sorry.
So we won't spend really too much time on this because this is very much like the our first function, which was the logistic function.
Mm-hmm.
It can be used interchangeably with the logistic function, and to be honest, from all the stuff that I've heard and from the lessons that I've learned, a lot of figuring out what the right activation function is looking at what some people did in papers and also a little bit of trial and error. There's not a lot of scientific evidence on when you should use it. It kind of changes from data set to data set, and the more you deal with neural networks, the more you might be able to pinpoint why you might want to use a tangent function or a logistic function.
Okay.
Next up, we'll have a rectified linear unit. Now, this is an output that is regression-like, and you can definitely understand why you'd want a value that predicts something between 1 or 0 and +infinity for any kind of prediction of numbers, stock prices, or housing prices.
So for continuous output variables.
Yes, thank you.
Right.
So this function is the rectified linear unit, or ReLU. The function here is f of z equals the maximum of 0, comma, z. And let's draw this. Z, I put my crosses, f of z, and this follows, it's always 0 until it goes past 0, and then it goes up at a 45-degree angle and is just equal to z after that point.
Okay.
So f of z itself is bounded by it's greater or equal to 0, and it's less than positive infinity, as z is greater than negative infinity and less than positive infinity.
Okay. So this function looks like the identity function y f of z is equal to z, except that because the minimum has to be 0. When z is negative, f of z is 0. It can't be any negative value. Yeah. Okay. All right. So Layne, you mentioned that this activation function is used for predicting continuous variables, continuous responses.
Especially when on our output layer, it will predict any continuous response because it's going to give you anything ranging from 0 to positive infinity. Now, it won't predict negative numbers. I actually haven't seen any instance of why you would maybe want to predict negative numbers, but maybe it's a matter of scaling your output afterwards. But this is, as it stands, just 0 to positive infinity. I actually suppose that on your output layer, if you needed negative numbers, you could not have a activation function. You could just say that z equals z, but it's typically, and especially in the hidden layers, you need this activation function. And one of the things that having this maximum 0, z allows you to do is make the non-linear representation. So the nodes have the ability to turn on at any value, but also turn off. And that's especially important when you're doing certain types of or exclusive or functions that you couldn't replicate using just a linear operation.
Can you expand on that a little more? Because I don't think I fully understand what you mean by that.
If we want in the next one, I can definitely go over an example of using XOR. I think XOR, which is the exclusive OR, is shown to only be able to work in a non-linear sense. You can't actually do it using a linear combination of things, and I can definitely do an example of that next time.
Okay, so stay tuned for the next episode in this multi-episode series on neural networks.